Before the 20th century, time was assumed to be universal. This was not a casual assumption. It was built deeply into classical physics. In Newtonian mechanics, time exists independently of space and matter. It flows uniformly, identically for every observer, regardless of motion or location. Whether an experiment is performed on Earth, on a moving train, or on a distant planet, the ticking of time is assumed to be the same. This assumption is encoded mathematically in Galilean transformations, where time remains unchanged when moving from one inertial frame to another. Space may shift, positions may transform, velocities may add, but time is absolute. This picture was extraordinarily successful. It explained planetary motion, projectile trajectories, pendulums, tides, and the behavior of mechanical systems with remarkable accuracy. There was no experimental reason to doubt absolute time for more than 2 centuries. Even James Clerk Maxwell's equations of electromagnetism, which unified electricity, magnetism, and light, initially appeared compatible with this framework. However, hidden within Maxwell's equations was a profound problem. They predicted that electromagnetic waves propagate at a fixed speed, determined solely by electric and magnetic constants of space. This speed did not depend on the motion of the source or the observer. In classical mechanics, speeds are relative. If a person throws a ball inside a moving train, an observer on the platform measures a different speed than someone inside the train. This velocity addition rule works perfectly for material objects, but Maxwell's equations did not allow light to behave this way. If light always travels at the same speed, then time and space cannot transform according to Galilean rules. Initially, physicists tried to save absolute time by introducing the concept of a luminiferous ether, a universal medium through which light propagates. Motion relative to this ether would then restore classical ideas of time and space. The failure of ether drift experiments, most famously the Michelson-Morley experiment, created a crisis. The expected variation in the speed of light due to Earth's motion through the ether was not observed. The result was not slightly wrong, it was precisely null. Light appeared to have the same speed in all directions regardless of Earth's motion. This was not a minor discrepancy. It directly contradicted the assumption of absolute time. Something fundamental had to give. The resolution did not come from modifying Maxwell's equations, nor from improving experimental precision, but from rethinking the structure of space and time themselves. The key step was the realization that the laws of physics, including electromagnetism, must take the same mathematical form in all inertial frames. If this principle is taken seriously, then transformations between frames must preserve the speed of light. This requirement uniquely determines a new set of transformations, the Lorentz transformation. The Lorentz transformation replaces the Galilean transformation by mixing space and time coordinates. Time is no longer independent, it becomes frame-dependent. For 2 inertial observers moving at a relative velocity v along one spatial direction, the time coordinate transforms as t prime equals gamma times t minus vx over c squared, where gamma equals 1 over 1 minus v squared over c squared. This equation is the precise mathematical statement that time is not absolute. The time measured by one observer depends not only on the time measured by another, but also on spatial position. Events that are simultaneous in one frame are generally not simultaneous in another. This is not a philosophical interpretation, it is a direct mathematical consequence. The transformation preserves the space-time interval s squared equals c squared times t squared minus x squared, which replaces absolute time as the invariant quantity. All observers agree on this interval, but they disagree on how much of it is time and how much of it is space. This single shift overturns centuries of intuition. Time dilation and length contraction are not separate effects, they are geometric consequences of the same transformation. Crucially, this equation does not arise from speculation. It arises from demanding internal consistency between electromagnetism and the principle of relativity. If time were absolute, Maxwell's equations would not be covariant. The Lorentz transformation is not optional. It is forced upon physics if light has a universal speed. Once time becomes frame-dependent, causality and simultaneity must be reconsidered. The equation shows that simultaneity is relative. 2 events that occur at the same time in one inertial frame may occur at different times in another. This is not due to signal delay or measurement error. It is a structural feature of space-time. There is no observer-independent notion of now extending across space. Time dilation follows directly. Consider a clock moving relative to an observer. The proper time measured by the clock satisfies d tau equals dt times the square root of 1 minus v squared over c squared. This shows that the moving clock accumulates less time between events than a stationary one. This effect has been experimentally confirmed using atomic clocks on aircraft, satellites, and particle lifetimes in accelerators. Muons created in the upper atmosphere live far longer than classical physics allows because their internal clocks run slower relative to Earth's frame. What is often missed is that time dilation is not a dynamical effect caused by motion acting on clocks. It is geometric. Different world lines through spacetime have different lengths, and time measured by a clock is the length of its world line. The Lorentz transformation encodes this geometry. Once accepted, absolute time becomes mathematically impossible. There is no universal parameter that all observers can share without contradiction. At this stage, time has already lost its classical meaning. It is no longer an independent backdrop, but a coordinate intertwined with space, dependent on the observer's motion. Yet this is still only special relativity. Gravity has not entered the picture. The deepest consequences are still ahead. The full meaning of the Lorentz transformation only becomes clear when space and time are treated as a single geometric entity. Hermann Minkowski recognized that the equations of special relativity are most naturally expressed not in separate spatial and temporal variables, but in a four-dimensional continuum now called spacetime. In this formulation, time is treated as a coordinate similar to space, except for its opposite sign in the space-time interval. The invariant quantity is not time alone, nor distance alone, but the space-time separation between events. In Minkowski spacetime, events are points, and the history of a particle is a world line. The proper time measured by a clock is the space-time length of its world line. Different observers slice spacetime into space and time differently, depending on their state of motion. What one observer calls space at a moment of time, another observer calls a tilted slice that mixes space and time. There is no preferred slicing. This geometric fact makes absolute simultaneity impossible. The relativity of simultaneity is not merely a side effect, it is central. If simultaneity were absolute, the space-time interval could not be invariant. The Lorentz transformation guarantees that causal structure is preserved. Events connected by light signals remain connected by light signals in all frames. This divides space-time into time-like, light-like, and space-like separations. Only time-like separated events can influence one another causally. Space-like separated events have no invariant time order. One observer may say event A happened before event B, while another may say the opposite, and neither description violates physics. Time, therefore, is not a global ordering parameter for all events in the universe. It is a local quantity, tied to specific world lines. This alone destroys the classical idea of a universal cosmic clock. When acceleration and gravity are introduced, the situation becomes even more radical. Special relativity applies only to inertial frames, but real physical systems involve acceleration. Einstein's key insight was the equivalence principle. Locally, the effects of gravity are indistinguishable from acceleration. This principle forces gravity to be interpreted not as a force acting in time, but as a manifestation of curved spacetime. In general relativity, spacetime is no longer flat. The geometry itself becomes dynamical and responds to energy and momentum. The metric tensor replaces the Minkowski interval, and proper time is given by d tau squared equals g mu nu dx mu dx nu. Time now depends not only on relative motion, but also on gravitational potential. Clocks at different heights in a gravitational field tick at different rates. This is not due to mechanical distortion of clocks, but because spacetime itself is curved differently along their world lines. Gravitational time dilation has been experimentally confirmed with high precision. Atomic clocks on satellites run faster than clocks on Earth's surface. Without correcting for this relativistic effect, GPS systems would accumulate errors of kilometers per day. There is no way to interpret these observations using an absolute time parameter. Each clock measures its own proper time, and no single time coordinate can be globally assigned without ambiguity. Even more striking is that in curved spacetime, global simultaneity generally does not exist at all. In many spacetimes, it is impossible to define a single time coordinate that smoothly orders all events everywhere. Time becomes a local concept, meaningful only along specific paths. At the deepest level, the failure of absolute time is not just a feature of relativity, but a structural constraint imposed by causality and geometry. In general spacetimes, particularly those containing strong gravitational fields, horizons, or singularities, time can behave in ways that have no classical analog. Near a black hole horizon, for example, time measured by a distant observer slows and effectively freezes, while the infalling observer experiences nothing unusual locally. Both descriptions are correct because there is no observer-independent notion of time. In cosmology, the expansion of the universe introduces yet another complication. A cosmic time can be defined only under very special symmetry assumptions, such as homogeneity and isotropy. Even then, this time is not fundamental. It is an emergent parameter tied to the large-scale motion of matter. On smaller scales, local clocks do not necessarily align with cosmic time in any simple way. At this point, time is no longer something that exists independently of physical processes. It is a measure of change along world lines, shaped by motion, gravity, and geometry. The original Newtonian concept of time as a universal flowing entity has no place in modern fundamental physics. What replaces it is not another absolute clock, but a network of local times, each tied to a specific physical path through spacetime. And yet, even this is not the final word. When quantum mechanics is brought into contact with curved spacetime, the very definition of time becomes problematic. In quantum gravity, time may not exist as a fundamental variable at all, but only as an approximate concept emerging in certain limits. When quantum mechanics is combined with relativistic principles, the status of time becomes fundamentally asymmetric. In standard quantum theory, time is not an operator like position or momentum. It appears only as an external parameter, something classical, something assumed. The Schrödinger equation evolves states with respect to time, but time itself is never quantized. This already signals tension. In relativity, time is dynamical and observer-dependent. In quantum mechanics, it is fixed and universal. The two frameworks disagree not on details, but on what time is. This tension becomes unavoidable when gravity is quantized. In general relativity, the geometry of spacetime, including time itself, is part of the dynamical system. When attempting to construct a quantum theory of gravity, there is no background time against which the system can evolve. The most direct canonical quantization of general relativity leads to the Wheeler-DeWitt equation, which has the form h hat psi equals 0. Strikingly, this equation contains no time variable at all. The wave function of the universe does not evolve in time. This is not an approximation or a mistake. It is a direct consequence of covariance. The absence of time here is sometimes called the problem of time in quantum gravity. If this equation is taken seriously, time cannot be fundamental. It must be emergent, a derived concept arising only in certain semi-classical limits. In this view, what we perceive as time is not part of the basic structure of reality, but a relational parameter that appears when subsystems are compared to one another. One way to recover time is through relational dynamics. Instead of asking how a system evolves in time, one asks how one physical quantity evolves relative to another. A clock is no longer an external parameter, but a physical system whose degrees of freedom are correlated with those of the system being studied. Time becomes an internal variable defined by correlations. In this framework, change exists without an external time parameter. The universe does not evolve in time, rather it contains correlations that give rise to the experience of temporal ordering. This idea appears in several approaches to quantum gravity, including loop quantum gravity and relational quantum mechanics. The flow of time becomes an emergent phenomenon tied to coarse graining and decoherence. Thermodynamics plays a crucial role here. While the fundamental equations may be time-symmetric, macroscopic time has a direction. This direction arises from low-entropy initial conditions. The arrow of time is not written into the laws of physics, but into the boundary conditions of the universe. Entropy increase gives time its apparent flow, even if the underlying equations do not distinguish past from future. Thus, even when time is not fundamental, it reappears as an effective concept at macroscopic scales. This does not restore absolute time. Different observers, different subsystems, and different coarse grainings can define different effective times. At the deepest known level, the question is no longer whether time is absolute, but whether time exists at all in the fundamental description of nature. In approaches such as ADS-CFT correspondence, space-time itself appears to emerge from more primitive quantum degrees of freedom. Temporal order can be reconstructed from entanglement structure rather than assumed from the start. In such theories, geometry, including time, is not basic. It is encoded in patterns of quantum information. The smooth flow of time experienced by observers arises only when these patterns satisfy specific conditions. Outside those conditions, the concept of time may lose meaning entirely. What began as a small inconsistency in electromagnetism has led to the collapse of absolute time at every level of physical description. From Lorentz transformations to curved spacetime, from quantum mechanics to quantum gravity, time is progressively stripped of its independence. It survives not as a universal parameter, but as a contextual, relational, and emergent quantity. A particularly radical framework where absolute time is impossible is causal set theory. Here, spacetime is not continuous, but composed of discrete events partially ordered by causality. The fundamental structure is not a metric or a coordinate system, but a causal relation. Which events can influence which others? There is no background time parameter. The ordering of events replaces time, but this ordering is not total. Many events are incomparable, meaning there is no fact of the matter about which came first. In such a structure, time is not something that flows. It is a bookkeeping device derived from causal relations. The familiar notion of temporal duration emerges only statistically when large numbers of events are coarse-grained. What looks like continuous time at macroscopic scales is an approximation, not a fundamental entity. This framework preserves relativistic causality without ever introducing absolute simultaneity. The key insight is that causality survives even when time does not. What remains invariant across all observers is not a time coordinate, but the causal structure itself. This suggests that causality, not time, is the true primitive of physics. Another deep indication that time is not fundamental comes from the role of symmetry. Fundamental physical laws are largely invariant under time reversal. The equations governing electromagnetism, classical mechanics, general relativity, and even quantum mechanics, with minor exceptions involving CP violation, do not distinguish past from future. If time were fundamental in the same sense as space, one would expect the laws to encode a preferred temporal direction. They do not. This raises a paradox. Our experience of time is profoundly asymmetric. We remember the past, not the future. Causes precede effects. Entropy increases, yet none of these asymmetries appear in the microscopic laws. This strongly suggests that the direction and flow of time are emergent phenomena, not basic ingredients of reality. From this perspective, the Lorentz transformation does more than abolish absolute simultaneity. It initiates a process by which time is progressively demoted from a fundamental role. First, it becomes observer-dependent. Then, under gravity, it becomes local. Under quantization, it disappears altogether. What remains is structure, correlation, and information. In information-theoretic approaches, time is reconstructed from the way information propagates and becomes inaccessible. Quantum entanglement plays a central role. The growth of entanglement between subsystems mimics the flow of time.
When a system becomes increasingly entangled with its environment, its state appears to decohere, producing classical behavior and a perceived temporal direction. This view aligns with the thermodynamic arrow of time. Entropy increase is not merely disorder, but the spreading of information into correlations that cannot be locally accessed. Time's arrow is therefore not a feature of space-time itself, but of information flow within space-time. In this sense, clocks do not measure an external time, they measure irreversible processes. Every clock relies on entropy production. Without irreversibility, time would lose operational meaning. This reinforces the idea that time is not a primitive variable, but an emergent one tied to statistical behavior.
The original equation that denied absolute time, the Lorentz transformation, now appears less as a correction and more as a warning. It signals that time cannot be treated as an independent universal parameter without contradiction. Each successive layer of physics confirms this message. Relativity removes global simultaneity. Gravity removes global time. Quantum gravity removes time entirely from the fundamental equations. What persists through all these layers is not time, but relations. Relations between events, between observables, between subsystems. Physics does not describe how the universe evolves in time. It describes correlations that allow observers embedded within the universe to reconstruct an effective notion of temporal order. At extreme depth, the failure of absolute time is tied to the way physical laws encode predictability. In classical mechanics, time parameterizes deterministic evolution. Given initial conditions at one moment, the future is fixed. This structure requires a global time variable that orders states uniquely. Once time becomes observer-dependent, the structure fractures. Determinism survives locally, but not globally. Different observers disagree on the temporal ordering of space-like separated events, yet all predictions remain consistent because no causal contradiction is allowed. This suggests that determinism itself is not fundamental, but conditional. It depends on the existence of a preferred time parameter. When physics abandons absolute time, it also abandons the idea that the universe evolves as a single state through a universal sequence of moments. Instead, the universe is better described as a static four-dimensional structure containing all events, with dynamical laws expressing relations between parts of that structure. This block space-time view is not an interpretation imposed from outside. It is a direct mathematical consequence of relativistic invariance. The equations do not describe becoming, they describe consistency relations between events. In this framework, change is not fundamental either. What we call change arises from comparing different slices of space-time chosen by different observers. Motion is not something that happens in time, it is a geometric property of world lines. The sensation of flow emerges because conscious systems are extended objects whose internal states are correlated asymmetrically along their world lines. This is why no physical experiment can detect the speed of time. There is no operational meaning to such a quantity. Time does not move, systems do. The Lorentz transformation eliminates the possibility of an absolute temporal rate by making time inseparable from space. Even attempts to reintroduce time through hidden variables or preferred frames fail unless they violate relativistic covariance. Decades of high-precision experiments have found none. At the quantum level, the absence of time becomes even more striking when considering path integrals. In the relativistic formulation, amplitudes are computed by summing over all possible space-time histories. These histories are not ordered by an external time parameter, they're weighted geometrically. Time ordering only appears when boundary conditions are imposed. This reinforces the idea that time is not a generator of evolution, but a label used to organize correlations. The fundamental object is not a trajectory evolving in time, but a space-time configuration contributing to an amplitude. In quantum field theory, particles themselves are not fundamental entities moving through time. They are excitations of fields defined over space-time. Creation and annihilation events are not processes occurring in time in the classical sense. They are transitions between field configurations. Again, time functions as a coordinate, not as a flowing entity. When horizons are present, the relativity of time becomes irreversible. Event horizons divide space-time into regions that cannot share information. For observers separated by horizons, not only do clocks tick at different rates, but the very definition of past and future diverges. Events that exist in one observer's future may not exist at all for another. This forces a reconsideration of what it means for an event to occur. Occurrence becomes observer-dependent. Physics no longer describes what happens absolutely, but what can be observed from within a given causal domain. In such contexts, time loses even its local universality. Proper time remains well defined along individual world lines, but there is no global structure tying these times together. The universe fragments into overlapping causal patches, each with its own internally consistent temporal ordering. At the deepest known theoretical edge, some approaches abandon space-time entirely. In algebraic and category-theoretic formulations of physics, the primary objects are not points or events, but relations and transformations. Temporal notions are encoded algebraically rather than geometrically. Composition replaces evolution. Ordering becomes contextual rather than absolute. In these formulations, asking "what time is it?" has no meaning at the fundamental level. The question is replaced by "what relations hold?" Time reappears only when these relations are organized in a way that allows for effective sequential description. Seen from this depth, the original statement that time is not absolute is not merely a relativistic correction. It is a clue that time is not part of the universe's foundational vocabulary. It is a derived language used by subsystems like us to describe patterns within a deeper, timeless structure.
At the Planck scale, the very assumptions that allow time to be defined begin to fail. Proper time relies on the existence of well-defined world lines, but quantum fluctuations of space-time itself destroy the notion of a smooth path. If space-time geometry fluctuates, then the metric that defines time intervals fluctuates as well. The quantity d tau loses meaning when space-time cannot be approximated as continuous. In this regime, asking how much time passes between two events is not merely difficult, it may be undefined. This is not a limitation of measurement, but of ontology. Time intervals presuppose a background geometry. If geometry is quantum, then time is not just uncertain, it is not a well-defined observable. This is why no operator corresponding to time appears naturally in quantum gravity. The absence of time is not a gap waiting to be filled, but a signal that the classical concept does not survive quantization. One of the most telling signs that time is not fundamental comes from renormalization. In quantum field theory, physical quantities depend on the scale at which they are probed. Space and time coordinates themselves are not immune to this. At very short distances, the effective description of space-time changes. Temporal ordering that is clear at macroscopic scales becomes ambiguous at microscopic ones. If space-time were absolute, it would be scale-independent. But every known framework suggests the opposite. Time is an emergent, scale-dependent parameter. At low energies, it behaves classically. At higher energies, it mixes with space. At the highest energies, it disappears into more primitive degrees of freedom. This mirrors the fate of other classical concepts such as temperature or pressure. These quantities are real and measurable, yet they are not fundamental. They emerge from collective behavior. Time appears to belong to this same category. The notion of evolution itself becomes questionable without time. In timeless formulations, physical laws do not describe change, but consistency. A law is a constraint that relates to different parts of the universe, not a rule that pushes states forward. Dynamics is replaced by correlations that must simultaneously hold. This perspective radically alters the meaning of prediction. To predict is no longer to compute the future from the present, but to infer unknown correlations from known ones. The success of physics does not depend on time flowing, but on the internal coherence of relational structures. This is why physics can function mathematically without time, even though human intuition struggles without it. Time is indispensable for experience, but not for equations. Attempts to restore time at the fundamental level often reintroduce hidden structures that conflict with observed symmetries. A preferred global time would break Lorentz invariance. A universal clock would contradict gravitational time dilation. A fundamental temporal direction would violate microscopic reversibility. Each attempt leaves observable scars that experiments do not find. The persistence of Lorentz symmetry across vast energy scales suggests that the absence of absolute time is not approximate, but exact. The universe appears to enforce this constraint with extraordinary precision.
Whatever replaces time at the deepest level must reproduce relativistic invariance naturally, not as a coincidence. From this viewpoint, the Lorentz transformation is no longer just an equation relating coordinates. It is the first crack in a much larger structure. It tells us that time cannot be separated from the rest of physics. Every attempt to treat it as independent leads to contradiction. Every successful theory weakens its status further. What begins as the relativity of simultaneity ends as the relativity of existence itself. Events do not simply happen, they occur relative to observers, frames, causal domains, and information access. Time does not order reality globally. Reality is locally ordered and globally constrained only by consistency. Even the language of before and after becomes emergent. In a fully relational universe, there is no absolute temporal ordering of all events. There are only partial orderings enforced by causality. Where causality is absent, temporal order has no physical meaning. This is not ignorance, it is a statement about reality. Thus, the deepest consequence of the equation that says time is not absolute is not time dilation or simultaneity loss. It is the realization that time is not the stage on which physics happens. It is one of the characters, appearing when conditions allow, disappearing when they do not.
One of the most unsettling implications of non-absolute time is that the universe does not possess a preferred present. In relativistic physics, the present moment is not a physical object, it is a psychological construct. There is no equation that singles out a universal slice of spacetime and labels it now. Any such slice depends entirely on the observer's motion. Two observers passing each other can disagree on which distant events are happening right now, and there is no experiment that can decide who is correct. This means the present is not something the universe contains, it is something observers generate. Physics describes events, not moments. The idea that the universe updates itself frame by frame is a cognitive projection, not a physical process. This leads to a deeper insight. Physical laws do not require time to pass in order to be valid. They require only consistency between events. When equations relate quantities at different times, they do not imply motion through time. They encode correlations across spacetime. The impression of evolution arises because observers occupy world lines and compare records stored in memory. Memory itself is a physical asymmetry. It depends on irreversible processes. Brains, computers, and measuring devices all rely on entropy increase. Without entropy gradients, memory cannot form, and without memory, the sensation of temporal flow collapses. Thus, the experience of time passing is inseparable from thermodynamic irreversibility. In a universe at maximum entropy, time would still exist mathematically as a coordinate, but it would lose experiential meaning. Nothing would change in a way that could be recorded. Another rarely emphasized consequence is that the relativity of time places limits on explanation itself. In classical physics, explanations often take the form, "this happened because that happened earlier." In relativistic physics, such explanations are frame-dependent for space-like separated events. What counts as a cause and what counts as an effect can differ between observers, provided no causal signal connects them. This forces physics to adopt a more subtle notion of explanation. Instead of chains of events unfolding in time, explanations become statements about allowed and forbidden correlations. The universe is constrained, not driven. Laws do not push reality forward, they restrict what patterns are possible. At an even deeper level, the loss of absolute time undermines the idea of a universal initial condition. In a timeless or block space-time picture, the universe does not begin and then evolve. The so-called initial state is just a boundary condition in a particular description. Other descriptions may place that boundary elsewhere or not at all. This reframes cosmology. The Big Bang is not necessarily the beginning of time in a fundamental sense. It may simply be a boundary beyond which classical space-time ceases to be a useful description. Time does not emerge from the Big Bang. Time emerges with the space-time regime that follows it. The relativity of time also constrains what it means to observe. Observation is not an instantaneous act occurring at a moment in time. It is a physical interaction extended along a world line. Measurements are processes, not events. This becomes crucial in relativistic quantum theory, where different observers may disagree on the temporal ordering of measurement interactions while still agreeing on observable outcomes. This consistency without shared time ordering is not accidental. It reflects the fact that physical predictions are invariant under changes of temporal slicing. The universe does not care how observers divide spacetime into past, present, and future. It only enforces causal consistency. There is an even deeper irony. While time loses its absolute status, proper time becomes more fundamental than ever. The only physically meaningful time is the one measured along a specific world line, but no two extended systems share the same world line. This means that even proper time cannot be elevated to a universal standard. Thus, the universe contains infinitely many legitimate times, none of which can dominate the others. Any attempt to privilege one is a matter of convenience, not ontology. Physics becomes radically democratic with respect to time.